Welcome back, everybody, and welcome back to the last session this semester. So, as usual, we will have the lab session after the regular session here. And I'm going to use the first lecture to discuss a little bit about the generalized adversarial networks, which is one of the final methods which we have included in this course. And I will try to link that with the other methods which we have discussed till now when it comes to generative methods. And so we're going to look at what these GANs are, a little bit about the mathematical formulation. So the method was actually developed by Goodfellow, one of the authors of that textbook on machine learning. And it started as a kind of game. So the inspiration is actually from gaming, where you have two networks which fight against each other, one which has the real data and one which produces fake data. And then it's to find the balance between these two networks. And in principle, in the beginning, these were actually devised as just neural networks which were competing against each other. So the optimization problem then ends up not being a minimization or maximization, as we've been discussing till now, but it's actually a minimization and maximization problem. And that has additional problems. And in the lecture notes and the slides here, we will not have time to cover all the additional details, but we want to give you the basic overview. And then in the slides, when you look at training challenges, evaluating GANs, etc., you will find additional tricks and hints on how you can optimize the training. So GANs have been there for a little bit more than 10 years, and they are extremely popular. So let me just use the slide a little bit in the beginning, and then we're going to jump a little bit back between whiteboard, the Jupyter Notebook, and the slides. So after some basic discussions of GANs, we are going to only briefly mention some of the variants which you have. And we are going to compare them with variational autoencoders, diffusion models, and also Boltzmann machines. And then finally, in the next lecture, we're going to have a summary of the course. So if we look at what we have done till now, excluding Boltzmann machines, so we spent quite some time on variational autoencoders, where we have a latent space, where the dimension of the latent space is much, much smaller than the dimension of the data which we feed in. So if you have a data which is defined by this dimensionality d of x, then the latent space is hopefully a space which then encodes the essential degrees of freedom in the definition of a probability distribution. Diffusion models, on the other hand, they keep the full dimensionality, and it's actually based on the estimating the lower bounds. And this is done t times. And we start with the full data, and then we denoise it, and then we reconstruct it, and then produce a probability distribution through that process. And then GANs, on the other hand, they're actually data sets where we have a fake data, Z, which is then defined by a degrees of freedom, K. And this is then competing with the real data. Then diffusion models, they are, as we have been discussing, they are just actually hierarchical variational autoencoders with T latent levels. And it has a fixed encoder and full dimensional latents. So when, as we discussed in the last 3-4 weeks, understanding the variational encoder is actually the fastest route to understanding diffusion models. Now, there is a additional thing here which I wanted to say a little bit about before we dive into the whiteboard a little bit and then back to the slides again. So here we maximize what's called the estimated lower bounds, and there's a variational inference. Here we have a fixed encoder and noise prediction. We also maximize in the same way, except that we do this t times. On the GANs, on the other hand, there is no likelihood bound. So the variational autoencoders and the diffusion models, what they give us is an approximation to a probability distribution which describes the data. The GANs don't give us a probability distribution. That's a big difference. So they actually, as you can see here, when we look at a variational autoencoder and a diffusion model, what we are doing then is that we are actually evaluating a probability distribution. GANs never evaluate that. That's a big difference. So in a way, we say that we define the probability distribution in an implicit way. The GAN, as it's set up, it was proposed by Goodfellow, one of the authors with Ben Jo and Co. Will, or perhaps one of the best books in the field. And it pits two neutral networks against each other in a zero-sum game. So there is an input, which is a noise, and it can typically be given by a Gaussian distribution or normal distribution. And this produces a sample X, which then is meant to fool the discriminator, which actually receives, let's say if you have an image, it receives the image data, and it produces a network which reproduces that one, but is trying to then to compete against the generator here, which then tries to fool the discriminator. So it implicitly defines a distribution, and the goal of the discriminator is actually to distinguish a real from fake. So neither network sees the other parameters, so you can just think of you setting two neural networks against each other, and they simply improve each other through adversarial feedback alone. So the way you do this is actually very simple. So this is a kind of schematic view of the architecture. So you have some noisy data, which can be generated by a normal distribution with zero mean and standard deviation of 1. It produces a data set, which is then compared with the one from the discriminator, which takes in the real data. And so this maps Z into the real data, the data space. And this one maps the image into this probability, which is then compared with the noisy data which is being produced. So the training alternates. You freeze G and update D, you freeze D and update G, back and forth. And you can derive mathematical limits on what you should get when you do the training. And you will see that when we look at the codes in the Jupyter Notebook for this week. So these are actually very interesting methods. And the reason for why they are interesting is that you can apply them to all types of situations. You can use it for unsupervised data, so there are no labels. And so that means that G learns simply the full data manifold. You can do it on supervised data, or you can do a semi-supervised, where you have a mix of labeled and not labeled data. So this is an extremely flexible method, and it has been applied to image synthesis, text-to-image translation, video predictions. It gives more blurred images than diffusion models. If you want very precise reproductions of images, diffusion models are the standard. And in scientific simulation, like in particle physics, drug discovery, and also climate modeling, these are methods which have been used. And for those of you doing particle physics, you may have encountered analysis of data set using GANs. So there's one thing I wanted to say before we actually look into the mathematics. So if you think of what we have been doing with this type of methods, which we call generative methods, we want in a way to find the probability distribution which defines the real data. This is normally unknown. So in a GAN, a general adversarial network, this is often the Z space, which you can call for latent space. This is often just model with just a noisy data. It could be some normal distribution multiplied with some parameter. And then we have the generator, which gives us a map from the data RK for the generator over to the discriminator. And then we have a generator distribution, which is the one which implicitly is there. The problem is, and I don't know if you have seen this equation at the bottom before. Are you familiar with that equation from statistics where you can relate to probability? So if not, I'm just going to show you a little bit on the whiteboard how you can actually get that equation. So in principle, if you have one probability and how the variables in the probabilities relate to each other, you can actually set up an inverse problem and find the other probability. So this is the ideal. This is actually the idea behind a method which we haven't discussed, which is called normalizing flows. And if you can have a simple model for the probability, this is something which you can actually do. It requires, however, that you calculate the determinant of that quantity which in general is not invertible and can be very multidimensional because the probabilities which we have live in many dimensions. So PG then is an implicit distribution, and it's normally accessed only through sampling. So we've been doing that with the variational autoencoders and diffusion models, except that then we have made an approximation to the distribution. A GANs only evaluates it implicitly, so you don't get the distribution function. So let's try to put these things together before we move on, okay? So that you can see the wood for the trees and how with these GANs actually do the training, and why we're actually producing that generator in an implicit way. So I could see that this equation is not fully familiar. So I just wanted to give you some of the basic mathematical details before we move on, because this allows me also to take a kind of a broader picture on the generative methods which we have been discussing till now. So after that, we will move to the next slide here. We are going to set up the algorithm, but let's just jump to the whiteboard in the meantime. So if we take a look at what we have done with generative methods, we typically split them into two broader classes: an explicit determination of the probability and an implicit determination. So let's just set up this, what we might call the generative taxonomy, generative methods. So we have one big set of methods where we deal with the probability distribution in an explicit way. So let me just write this as explicit. So that means that we are then able to set up a probability distribution. And if we think back to Boltzmann machines, what we had then was a probability distribution which was proportional to the E. So let me just try to make this box a little bit bigger. E, and then we had some function of X and theta divided by a normalization constant. Now, as we saw, this is actually something which is not very tractable. So what we often need to do then is to make approximations, or we can use tractable methods. So when we do approximations, the methods which we have looked at till now are Boltzmann machines, where we defined what was called a contrastive divergence, which is the way we optimize the probability distribution. We have variational autoencoders. So these are some of the more popular methods. And then we had diffusion models. So we make an approximation to the probability distribution by optimizing. So what we are doing then is actually we are taking del theta of log of p theta of x, and we want to drive that one to 0. This is the function we are optimizing. And we make approximations. So the variational autoencoders, the latent space is typically just given by a Gaussian. Now then, if we look at the explicit methods, we also have, instead of approximations here, so let's just highlight the approximations. So this is the methods. But then we also have what we will call tractable. And one of the standard methods here is actually a method which we haven't discussed, which is normalizing flows. And I mark it in red here because we have not covered that one this year. And in this specific case, what we actually have the possibility to do is to solve this inverse problem, which I'm going to put up on the next page on the whiteboard. So these are the so-called explicit methods. But then we have the implicit methods, and the generative adversarial networks are examples of implicit methods. So that means that if we have an explicit method, it means that we have a model for the probability distribution. The only problem is that these probability distributions, which you see here, they are normally multidimensional. And even if I give you an analytical expression for it, it can be very difficult to deal with numerically because you have so many degrees of freedom. So the other class of methods, which we typically have when we look at generative methods, are the so-called implicit methods. And the implicit methods, those which we have encountered till now, are, or which we are going to discuss today, one of the more popular ones are actually GANs, generative adversarial neural networks. There are actually other methods as well, but we will not mention that here. So these are normally called methods based on Markov Monte Carlo chain methods, etc. So GANs, so the kind of methods you see here, I have left out autoregressive methods, which also deal with tractable probabilities. The typical methods, which are among the most popular ones when you look at generative methods, are Boltzmann machines, variational autoencoders, diffusion models, normalizing flows, and GANs. So let's take a look at that expression which we put up on the slides. And you may ask, I mean, where does this expression actually come from? So suppose now that you have a variable z, which is given by generated by a probability distribution, z. So z, the z which you see here is the one which defines a domain. And then you extract, so this should normally be an uppercase letter. So I hope you can see this is normally an uppercase letter. And the z itself is just a stochastic variable. Then the thing with the, for instance, normalizing flows is that this P of z is known. So normally what you assume is that this guy here is known if you want to use a tractable method like a normalizing flow. The problem we have with typically with the variational autoencoders and diffusion models is that we have to make a model for it. Then what you also assume is that there is a variable x which is related to z via a function, where this function f is actually a function which is invertible. So f of x, where f is an invertible function. So then you can actually define a probability distribution for x. So we can then define a PDF, probability distribution for x. So we know that P of z is a probability distribution. So PDF for x in terms of the probability distribution for z. So this is actually an exact relation you can obtain by requiring that probabilities are conserved. And this is an obvious statement which you impose on probabilities, because if you make a change of variables or a change of probabilities, there is no way you can find a probability which makes you a lotto millionaire, period. So the probability of becoming a lotto millionaire is the same, whatever. So that probability is conserved. And you can think of finding smart probabilities which can give you an access to immediate fortunes, but this is never the case. So the assumption that probabilities are conserved is something which is fundamental for deriving the equation which comes now. So I just wanted to state this because this deals a little bit with the type of problem we can solve in case we have a known probability and we can have a function relation between x and c where the function is invertible. And that leads, for instance, to generative methods like normalizing flows. This is not the case when we deal with variational autoencoders, diffusion models, GANs, etc. So I just wanted to bring this up because there is a whole plethora of generative methods which are being used. So if that is the case, then we can define a probability of X, the domain X, the uppercase letter is the domain of variables for the stochastic variable X, which is now defined in terms of this probability. And we know that if the function is invertible, then this means that we would have F minus of X. So this just goes back to this one where we have assumed that the function is invertible. And then this is then multiplied with the absolute value of the determinant of second derivative of this function f with respect to x. Now, you may ask, where does this actually come from? So the whole thing actually comes from conservation of probabilities. So what we've said is, so this equation, if you have a known model and you know this function, or you can train this function and it's invertible, then you can actually attempt at finding the probability distribution. So let me try to explain to you what is going on here. So if you think of x, which is now given by this function f of x, which is of z here, which is an invertible function, then we know that if that is the case, if invertible, and I'm going to show you some simple examples of these cases here. So if invertible, then you have that c is equal to f minus 1 of x. And I will show you an explicit example which you probably have encountered before. So the basic rule which leads to the expression which you have here is the basic assumption that probability is conserved. So probability being conserved is assumed to be conserved so that means the following, that P of x multiplied with d of x. So let's assume that these are continuous probabilities. What that simply says is that this is a probability of finding x in a domain from x to x plus dx. This is the way you read that expression. And this is a typical expression you will find in statistics textbooks on probability distribution functions. Then we should then, since probability is conserved, a smart change of variables should not change probabilities. Okay? This is like energy is conserved. You often find a calculation you can do in another reference frame, which allows you to make the calculation in an easier way. And with probabilities, this is actually one of the basic relations which you use to make, for instance, random number generators. Because the random number generators are given typically by sequential algorithms, which then again means that you often have a basic algorithm which gives you the uniform distribution. Now, if you assume this, then in one dimension, so let's just stay in one dimension here, in one dim. One dimension, since z can now be written in terms of this function f inverse, what we get then is actually p of x equal to p of z. And then I have f inverse of x. And then I have the absolute value. We don't have negative probabilities, obviously. D of z, we divided with d of x. And then I can use again this function z being given by f inverse. So I would put in f inverse in here. So if I do that, what I get then is the following expression. So I would get a p of x equal to p of z f minus 1 of x, and this is given by d of f of mine inverse of x of d of x. In several dimensions, what you end up then is a Jacobian, because f is then a function of many variables. So in several dimensions, what you end up with then is actually a Jacobian matrix, and then you have to evaluate p of x by evaluating the determinant. And that is the general expression which relates two probabilities to each other. And this is typically given by the determinant, and then I have to set up the Jacobian matrix of d of x. And equivalently, you can find a corresponding equation. Since we have since you would have that d of f inverse of d of x is actually equal, and this is not so difficult to show, of d of c of minus 1. You can then actually replace this with p of x equal to p of z as a function of z, and then the determinant of d of f dc inverse. So this is just an alternative equation. Now, if you can do this, if you have such a function f, then this is a typical case where you can now set up a model where you have a tractable probability. But that means that one of these p of x or p of z's have to be defined by a probability which you can handle easily. So keep in mind that your probabilities distributions are typically multidimensional animals over many, many, many variables, and they can be difficult to evaluate. And that's why we have methods where we deal explicitly with the probability distribution, but we make approximations. Normalizing flows start with this equation here. So as a final thing, let me just show you an example which you probably have seen before. So let's now assume that this probability P of z, and this is the case you actually have when you deal with random number generators. So if that is given by the uniform distribution with c between 0 and 1, this is equal to dz when z is between 0 and 1, and is 0 else. Now, what we would like to have now is the relation to this function f, which I put up here. So let's say now that I don't know this function f, but I know the probabilities. So you can say, I know the probability p of z, and I know this function. Alternatively, you can say, I know this probability and I know that probability. And then I don't know the function f. So let's just look at an example here. So suppose now that this p of x of dx is actually the exponential distribution. And in that specific case, what we have is that x lives between 0 and infinity. So the question then is, what is f of x and f of minus z? Okay. This is a typical situation because in all random number generators, they are given by a uniform distribution. That's the basic algorithm which is being used. And then when you have a uniform distribution, you have to make a mapping. And that mapping is something you get, again, from the conservation of probabilities. So we simply require that pz of z of dz, which in our case is just dc, is equal to p of x of d of x, which is then equal to e of minus x of d of x. And then I integrate. So when I integrate now, I get something which is called the cumulative distribution. So if I integrate here, I can actually define a function z of x, which is given, so this is our f of x actually, which is then given by 0 up to x of p of x prime of d of x. And we know that in our case, this p of x, this is actually what you see here is called the cumulative distribution. And I'm simply going to call this with an uppercase p of x. So this z of x is actually equal to our p of x, the cumulative distribution, that's the definition of it. And that is given by 0 up to x. And now I put in the exponential distribution of d of x prime. And we know that this is pretty trivial to solve. So this is e1 minus the exponential of x. So that's the function. And then I can invert it, right? So the inverse gives x of z is equal to minus the logarithm of 1 minus z. And you see now that if z is equal to 1, that means that x is equal to minus ln 0, which is plus infinity. And if I put z equal to 0, then I get ln 1, which is equal to 0. So x lives between 0 and infinity. So what I have here now, since in this particular case, I already had a model for the probabilities, but I didn't know the function which is invertible. So this function is actually pretty easy to set up. And this is actually the mapping you use when you call a random number generator for the exponential distribution. So that calls the uniform distribution and then performs the mapping and then gives you the random numbers which are generated according to the exponential distribution. So this was a case where what we did was to assume in this equation here, we actually assume that we know this one, we know that one, but we didn't know this one. What you often have the situation when you use normalizing flows, which we mentioned in the very beginning here, normalizing flows here, is actually that you have a model for this probability P of Z, and you have a model for this function F. And then you can define the probability. So let's see, if we now go back to these different methods which we have been dealing with, you see now that the class of explicit methods where you make approximations leads to these very popular methods here, where we, in one way or the other one, we are actually optimizing this quantity. This is the quantity we want to drive to 0. Then, if we do tractable ones, for the tractable probabilities, we need then to be able to compute this equation here. And that is the basic recipe behind normalizing flows, which we haven't dealt with. Then, the last topic which we will deal with in this semester is actually generative adversarial networks. And that's the final method. And in that case, we are not interested, we actually never deal with a log of P, but we have an implicit way of looking at it. So I hope you, with that figure which you see here, the reason why I brought up some of these technicalities today was simply because that gives you the kind of way to relate to what the different methods actually stand for. And we will repeat some of this in the next lecture when we do a summary of the course. Okay, any questions so far? So let's go back to the whiteboard and take a look at the basic machinery for generative adversarial networks. Now, in the codes, which you have in the Jupyter notebook, what I have done is actually just to take a simple generative adversarial network, which then what it does is actually implements two neural networks which fight each other. So let's bring up this one and stay a little bit with the whiteboard till after the break. So what we are doing then, and this is what was proposed by Goodfellow, is that we have a minimization and maximization problem. So the whole thing, just to remind you quickly, if you look at this image here, so we create a network which is meant to fool the network which trains the real data. And then this is the discriminators then meant to discriminate what the generator sets up. And there is a kind of zero-sum game between these two. So that at the end, we've trained the discriminator so that we can actually, and the generator, so that we can actually reproduce the data. But we don't produce a probability distribution. So what we are doing then is that we are calculating two expectation values. This is the optimization problem. So we want obviously to optimize this one. So this d of x is meant to mimic a probability distribution. And then we want to minimize the difference between the d correct on a fake value g of c. So the discriminator maximizes v, this function, and the generator is meant to minimize it. So when this d with the input from gz is equal to 1, then we are fooling the discriminator. So this quantity defined in terms of the real data is actually a constant with respect to g, so g actually doesn't see that. So g minimizes actually the difference between the two. So it's a minimization and maximization problem. And this is often a type of problem which can be numerically more difficult. And these are two probability distributions. So this P of Z is then something which is done on the fake data, and D of Z is actually produced on the real data. So the problem which you then find is that you can have some non-saturating problems. So if you look at the original objective, so early in the training, this D is strong. So that means that the probability of being cheated is actually close to 0. So that gives you a log 1, which is close to 0. And then the gradient vanishes before G has learned. So instead of minimizing this 1 minus D, one maximizes just a log of D. So there are many kind of small, subtle things when you're setting up the equation. So in order to avoid that you end up in this equation where you basically have no training, you, instead of minimizing, so it's set up as a minimizing maximization problem, but you end up in practice with maximization. Because this is actually the function you want to set up. And the typical loss form, which you see then, is that when epsilon is close to 0, then you would have a log of 1 minus epsilon. You get a minus epsilon, and which is small. And then the log of epsilon can then lead to 1 over epsilon, which is large. So when you train, so you have alternating gradients. So you have one neural network. This is the way actually Goodfellow set it up back in 2014. So then you freeze G, and then you do a gradient ascent on D. And then you freeze D, and then you do a gradient descent. One is a maximization problem, and another, in principle, a minimization problem. And the fake images, if you're training on images, are detached from the computation graph during the D step to prevent spurious gradients which are flowing into G. So both networks update simultaneously, but that in general does not guarantee convergence. So there is a kind of balance here, which is gives us a hint on how we can derive the optimal discriminator. So keep in mind that these are expectation values. So these are expectation values now where we can use X, the real data. So we have this probability and log D of X plus this probability P of G for X. So we have calculated X using the variable Z from the generator. And then we have 1 minus D here. What you can do then, if you look at each X independently, you can maximize this integrand, where what I've done now is simply to take these terms and relabel them as a log of T. and B log of 1 minus t, where A is this probability, B is this probability, and t is just d of x. Then I take the derivative here just to find the optimal setup. And if I take the derivative, I actually find that this t is equal to the probability of A divided by A plus B. You can check that the second derivative gives you a maximum. So, and that is the case. So the kind of optimal discriminator is actually what is something called the Bayes optimal classifier for two-class problem. So these are the two classes. These are the data sets, and this is the fake data, and so real fake, and under equal priors, actually. So this is a problem, and this means that when you have equilibrium, when PG is equal to P of R, then you have a relation for the optimal D, which is just given by a half. So that means that the discriminator cannot distinguish real from fake. It is reduced to random guessing. And the loss function at equilibrium then, if you then substitute it, you will find that the value which it should reach at equilibrium is actually minus 1.2 times log 2. So in practice, what you will see also is that we monitor d of x and this dg of x during training, and both should converge to 0.5 at equilibrium. So if this is much, much smaller than 0.5, the generator is losing. If d of x is much, much smaller than 0.5, then the discriminator is failing. So it's a very, how to say, it's a kind of very intuitive thing to do here with this. You can just pit two neural networks against each other. And I can show you an example of a code here before we take a small break, and then continue along these discussions of GANs. So a typical example, so if you go to the Jupyter notebook, you will find an example which is actually taken from the Rashka's textbook. You will find some of the definitions which you had in the PDF file, just a kind of repetition of what we have seen. But I just wanted to show you the typical setup of a GAN here. So you can, so this is the GANs applied to the MNIST data. I'm coming back to some of the technicalities. So we actually have two neural networks. So this is the simplest possible. And what we are optimizing is not the Kullback-Leibler divergence, but it's something which is called the Jensen. It's not one of my relatives, Jensen-Shannon probability. And we are coming back to that after the break. So what you can see then, if you look back at this model here after training, so you will see this is on the MNIST data. And on the MNIST data, when you visualize things, you can then see the generator loss and the discriminator loss. They stabilize after a given number of iterations. And if you look at the values, you will see that they are getting close to 0.5 after a given number of iterations. And then if you look at the, after one epoch, this is what your image looks like. It's pretty blurred. But then gradually, you're able to reconstruct after 100 epochs, you see that this is most likely, I guess, a number 9, 1, 3, 4, and 9 here. So this is a typical example of an application of the simplest possible MNIST. Now, for image recognition, what people often do is that they use convolution neural network with GANs. So you pit two CNNs against each other. Let's go back to the slides. Now I have to find my, okay, I forgot one thing, because if I don't do that, it doesn't see it. So you saw from that code example, which is in the Jupyter notebook, where we just pit two neural networks against each other, that you, after some time, you reach this kind of equilibrium situation here after a given number of iterations. So this will be the typical loss function at equilibrium. So after the break, we are going to look at the kind of functions which we actually end up optimizing. So when we discuss variational autoencoders and also Boltzmann machines and diffusion models, we encounter this Kullback-Leibler divergence, which in case P and Q are equal, then this is exactly equal to 0. So it's a positive number, and it's actually used in the optimization of probabilities. And that leads to what we, with the variational autoencoders and diffusion models, called the elbow, which means that gives us an elementary lower bound. The problem with this function is not symmetric, and what people have introduced is something which is called a Jensen-Shannon. This is what is implemented in that Jupyter notebook, and this is the quantity you would typically optimize. So it's symmetric, non-negative. You can show that it's bounded between 0 and log 2 for any P and Q, and it's also related to the total variation. So what you end up doing then, when you do the algebra here, is that when you expand it and simplify a little bit, then we're putting in these limits, which we found from the previous case, and this recognizing these quantities which we put up, you can actually find that the GAN minimax objective is equivalent to minimizing this so-called Jensen-Shannon divergence between the probability which represents the data and the probability of the generator. And the global minimum is -2 times log 2 is achieved when the two probabilities are the same. So this is in the training, and you saw that also from the results that we actually approach this limit of 1/2 for both the two generators G and D. So I see I'm a little bit over time. I'm going to say a little bit more. There are many technicalities with GANs, how you can train them, how you can improve on their convergence, etc., etc. These are technicalities which I placed in the slides. Feel free to take a look at them, because this is also how you would use them. And then I will skip many of these small technicalities. We are going to look at the pros and the cons, and then we jump into a final summary of what we have done this semester. So as I mentioned before the break, the code which you have in the Jupyter notebook for this week implements simply two neural networks which fight each other. And it implements the Jensen-Shannon divergence instead of the Kullback-Leibler divergence. And this has actually an objective which is has a global minimum, which is -2 log 2, which is achieved when the two probabilities are approaching each other. And this is something which we saw from the calculations. After 100 epochs, we saw that the two probabilities would actually stabilize to a value of 1/2 each. And this is a kind of typical result which you would plot when you're dealing with a GANs. Actually, you would plot this feature here when the global minimum is approaching the desired value. Now, you can do much more here, and there are many technicalities. So the typical way of setting up the loss function for the discriminator part is, and you will see that in the notation here, you would have a loss D for the discriminator, and then you would have the generator loss, which is just given by the function D, the log of the function D, and a minus, as we saw from the previous equations, and then with a D, which is then given by G and Z as input here. Now, there are many small tricks which are being used in these calculations. So this divergence here, when they have non-overlapping values, which is common in early training, then we get that this Jensen-Shannon divergence is close to log 2 constantly, which gives 0 gradients elsewhere. There is something which then is included, which is called the Wasserstein distance, where you actually optimize with, or you include this optimization here, and where you have the sum of all Lipschitz 1 functions, which are functions whose difference doesn't increase more than just a factor 1. So the there are many ways of, as I said, dealing with it, and I leave these as small technicalities which you can look up. The basic setup of a GANs is pretty straightforward, but then there are many things with the vanishing gradients which can take place. As I said, when D is perfect early in training, then the D of X is close to 1. And then that means that the D of G is actually equal to 0. And that means that the original gradient actually approaches 0. So there are tricks which you can then use to avoid vanishing gradients. I'm going just to leave this as something you can look up if you want to dive into GANs. It's not that important now. The most important thing is just to have the basic concept. But I wanted to come back a little bit to the comparison between these different methods. So we have looked at mainly 3 big families of generative methods. As I said, we have not covered normalizing flows. And if we look at the variational autoencoders, what we are optimizing then is actually what we call the elbow, this lower bound. And the same thing is done in the diffusion. It produces a likelihood, a probability distribution after training. And we can use that probability distribution to generate, let's say, new images. A GAN does not do that. So here we have a minimax of this Jensen-Shannon divergence. I didn't put in Boltzmann machines here, but in Boltzmann machines, what we do is to optimize the log of the probability distribution. And we get 2 terms, one which is the data-driven term, and then the other one which is the expectation value of the log of the function which enters the probability distribution. So we have a compact, for variational autoencoder, we have a compact latent space. So the whole idea, and if you remember some of the runs we did 2 to 3 weeks ago, you saw that we could actually represent the MNIST data with basically 2 to 3 degrees of freedom with a latent space. So this is very compact, whereas when we do the diffusion model, we have a full dimensional latent space, and we do this many, many times. Here we just have the noise, which is the latent space, and that noise can have large dimensions or small dimensions. It's actually you who define the neural network there. So the encoder part, so this is learned, whereas in the diffusion model, it's actually a set of fixed denoising approximations where you propagate the values according to a fixed formula. Here, there is no encoder at all. There is one decoder pass, whereas in the diffusion set, we actually do a set of T steps in order to denoise the probability and then to reconstruct it again. In the GANs, we just have one pass between the discriminator and the generator. The stability is normally high. With the GANs, it can be low and moderate. The sample quality, as you also saw from the variational autoencoder runs, can be moderate, sometimes not very impressive if you train a small model. Whereas with diffusion, it's what we normally call state-of-the-art, if you want to, let's say, generate new images. However, diffusion models are expensive to train. So if you try to run some of the examples we have for the MNIST data in the Jupyter notebook from last week and the week before, you will see that the diffusion model actually takes a lot of time to train. Actually, that code which I have, if you don't have access to GPUs, it takes hours, the setup which I have, because it runs on my laptop, which only has CPUs. Well, I have an old laptop, I have to buy a new one. Actually, the big difference, which you see now, when it comes to many of these models, is who has access to GPUs and who has not. That's what makes a big difference. So the mode coverage in diffusion model is normally excellent. Anomaly detection, you have possibilities for that in variational autoencoders diffusion, but not in GANs. So they all have their pros and cons, but the standard method, which is normally the chosen one, is normally diffusion models nowadays. So mathematically, what we do with the variational autoencoder is that we are optimizing this quantity here, so which is proportional to the expectation value of the difference between x and the x which is produced now by the latent space. So the posterior has non-zero variance, and then the decoder learns the posterior mean over all likely competitions, which is a blur over the data manifold. So diffusion avoids that by predicting only the noise, which is added at a given step, not the full image. So the variational autoencoder tries to predict the full image, and each reverse step makes a small committed correction, and that's the diffusion part of it. The GANs are normally avoided by replacing this L2 loss with an adaptive learned discriminator loss, and that typically penalizes blurriness and any systematic deviation from real data. And that's, so GANs, as you saw after 100 epochs in that code from the last lecture, you saw that after 100 epochs, we were actually reconstructing the full image. I want you to keep this in mind, as we mentioned before the break, when we look at these different models. So variational autoencoders and diffusion models, they actually optimize a lower bound on this log P as a function of the parameters. So they can both generate and evaluate a probability distribution. The GANs have no access to the probability distribution. So in many applications in the physical sciences, whether you do chemistry, physics, mathematics, and so on, you often want to have the probability distribution. If you think of a standard neural network, a neural network does not give you a probability distribution unless you use it to solve differential equations where the solution can be interpreted as a probability distribution. So if you use a neural network to solve Schrödinger's equation, then the neural network gives you the wave function, and the wave function squared is a probability. So, but in general, neural networks do not give you a probability distribution. That means that if you want a probability distribution, you would have to reconstruct it by making many, many runs, find confidence intervals, etc., to build up a model for the probability distribution. This is what normally discriminates between discriminative models and generative ones. So with a neural network, what you typically do then is to fit a function, you make predictions, and you can find correlations in the data set. But when you have a probability distribution, you can do that as well, but you can also estimate the standard deviations, and you can study causality. What is the probability of A given B? So a probability distribution is often closer to the way we want to model data from the physical sciences. So you can see now the consequences of no likelihood. You cannot compute log likelihood scores for anomaly detection. You cannot evaluate model fit on held out data in a principled way. Evaluation requires proxy metrics rather than test set log likelihood. And you cannot be embedded as a prior in a Bayesian framework. And in statistics, I don't know how familiar you are with it, but in statistics, you often have this distinction between a frequentist approach and a Bayesian approach. The Bayesian approach, in a certain sense, is what gives you the best of both worlds, but it is often more complicated to implement. So there's always a pro and con, depending on what kind of approach you're interested in. So like if I look at myself, what I'm doing, I'm mostly interested in probability distribution. So I try to extract the best from a frequentist approach and the Bayesian approach. So these are important things to keep in mind when you are deciding upon what kind of method you're interested in using. So there are some other pros and cons here, why this is a price worth paying sometimes. So in my case, I'm interested in having an estimate of the errors as well. And I'm also interested in causality. If you're not interested in that, I mean, you can say that the discriminator provides a perceptual loss that no fixed probability can replicate. It adapts to what looks real, to a neural network in that case, which you're pitting against each other. It captures textures, sharpness, and high frequency detail. And sometimes this standard approach with variational autoencoders and diffusion models, they actually don't approximate that well enough. So I put this up against each other, and you can use this as a kind of guidance for your own applications. So typically, the elbow, which is this lower dimension, this lower bound, is a well-defined scalar. Both networks trained with standard stochastic gradient descents work well, and the Kullback-Leibler divergence prevents collapse when weighted correctly. Main challenge is actually choosing the parameters for this variational autoencoder. Diffusion model is normally stable. There is no adversarial dynamics. Main challenge is noise, but also runtime. So I didn't put that in here. Runtime is a big challenge. So if you want to run diffusion models, you need to have access to a good setup on high performance computing, which means nowadays means you having access to GPUs. If you haven't done it yet, get an account on the UIO machine learning nodes. So everyone with a UIO user account can get access to these. They have some older NVIDIA graphic cards, but they're still much better than your standard CPU. So you just search UIO ML nodes, and that normally gives you access. And probably some of you have access to this in your research group as well. But keep in mind that if you use other resources, like we have in Norway, we have a national entity which controls all high performance computing facilities, which is called Sigma 2. Then there's a price tag of 5 Norwegian kroner per GPU hour. So there are also some other things like the variational autoencoders. The decoder must explain all data for a single mean. So sometimes the generated images are averages over the data manifold. They can be blurry. And the model covers all models, but fails to commit to any one of them. So that can be a typical problem. The diffusion then avoids the problem which you have with mode collapse and also the so-called posterior averaging in variational autoencoders. And that typically prevents the collapse just into one of the modes. So take a look at some of these slides here. There are some detailed pros and cons of variational autoencoders, diffusion models, etc. I just leave that here, and then I have a list of when to use each model, but this is something which I'm going to repeat pretty soon now when we look at the course at a glance. So I wanted to use the last half hour to remind you of some of these things. So you will find a summary about the variational autoencoders, diffusion models, and the GANs here. But you will also find it at the end here when we look at the course at a glance of what we have covered in this semester here. So the models which we have discussed, we haven't done everything in full detail, but we discussed feed-forward neural networks. We've discussed the physics-informed neural networks, CNNs, which many of you are using. We have recurrent neural networks. We discussed autoencoders, and we had a brief excursion into transformers. So the problem with a course like this one is that many of these topics, when you look back 2 to 3 years ago, it's almost like looking back in doing archaeology, because the field is moving so quickly that there are topics like agentic AI, which is a course by itself. And in the at the GitHub address of the course, there's a link to another course on agentic AI. And if you're interested in that, please take a look at it. We're actually going to develop a new course next spring on agentic AI for the physical sciences. So stay tuned, because this is really what things are moving. And you will find some perspectives here, because you can see that the topic here, we've simply decided to look at discriminative models, because many of you do actually use CNNs. I know that people doing CERN data analysis, I mean, CNNs are very important. The same with people looking at time series. Autoencoders are very popular ones, transformers as well. And also these generative methods. So if you're looking at the diffusion models, which are the kind of state of the art, there, yeah. About that, I will say a little bit at the end here, actually. But it will be mainly reinforcement learning. Reinforcement learning is a part of agentic AI. So it will include reinforcement learning. And then we are going to look at how you can interface, let's say, a theoretical model with an experimental setup. And that's where agentic AI really comes in. So, as I said, I mean, just 3-4 years ago, when I developed this course material, this was brand new. Reinforcement learning has been there. And everybody was then talking about diffusion models and GANs. So the field is actually a field which is difficult to keep ahead of. And as a kind of small digression, many of you actually a little bit in doubt whether you should use large language models like those provided by Anthropic, OpenAI, Google, etc. So my advice is actually, and this is what we've been pushing in this course, is actually use these as much as you can. So the Claude Code is actually, many of the lectures which you see here, I had all the material written up, but the codes were not consistent with the lecture material. So I had different notations in the codes. So what I did was actually to take step by step. You cannot put everything into it like a cauldron and then you keep boiling, but you have to do it in small steps. Then it does things correctly. You can just ask it, take my Jupyter notebook and my LaTeX notes, synchronize this for me, please. Make it coherent. So my modality then, my way of doing this was actually to print out all my slides. I would spread them out over the floor. I would have the codes, and then I would look at, okay, here I use another notation than I have in the lectures. And then this would typically be one full day. When I use these tools, as long as you bake in step by step, you can actually become much more efficient. So these are actually tools which make life much more efficient. And then you can address more important topics. There's another aspect of it. So what I often do when I have developed a project, I have written a document, let's say a scientific article. And then I could ask, can you give me some hints on how we can use this in other projects? So normally you have some ideas of how you can go on. But then in a field like the one I'm working on, which is more quantum technologies and machine learning coupled with that, you have typically on Arxiv, this preprint server, there are up to 100 new articles every day. There is no way you can keep track of that. There's no way. I barely get time to read the abstracts. And I always take a note. I mean, I should read this paper more if I have time. So what Claude, for instance, does for you when you ask it, can you give me some hints on what I could do further? It actually goes through the existing literature. And in my cases, I've had often hints on 3-4 new things which I haven't thought of because I have not seen those scientific articles. So it's a great way to actually survey the literature, but you have to be careful because sometimes it comes up with just that you really have to be careful. Huh? So, but if you do these things progressively, step by step, you can actually develop a large program suite which tackles advanced problems. So if you have not used them, this actually, I've been repeating this again and again, often in the lectures, use these softwares because they actually improve your efficiency and they give you access to much more information and then you have to digest it. So let me ask you, who is not using it? Good, that's a good point. Excellent. I actually get comments from many people, they are afraid of using it because you had all these discussions about cheating and so on. But this is actually a course where you don't, if you don't use it, you actually get penalized in the sense that you get much less done. Yeah.
I have maybe like for code development
Yeah.
and suggestions
Yeah.
specifically. Is it something that we need to disclose, basically?
Yeah, yeah. I actually want to. This is a very good point because we want you to, when you use these tools, you should write it in the report. I've used it to debugging. I've used it to. I've asked for suggestions on how I can improve my code, what I can add, and so on. So that's. It's very important because many of you are in the beginning of your studies. And then sometimes it's difficult to see the wood for the trees because there are so many possibilities. And these softwares are actually getting better and better. And I'm not paid by Anthropic, but I would say that Claude Code, for me, is actually the one which has given me the best solutions for programming. Really, it has. But I've been baking in, like I had a huge C++ library, where my research pipeline was inefficient because I would write to file, and then I would find in the matplot library, would find ways to plot it, and then I would scatter the plots, and then I would look at the plots back and forth. And then you can simply bring these all together in a Jupyter notebook and ask it to find ways to plot it, which exemplify the results in a better way than you cooked up. So instead of you spending days in finding a matplotlib library example which fits your case, this does it for you in just a few minutes. And then you can focus on the interesting science. Okay, sorry, this was a digression, but I think I wanted to repeat it because these are tools which you should actually use critically, as always. So you see a little bit what we've covered through the semester, and the autoencoder part also enters the variational autoencoder part a little bit. But these are basically the topics which we have covered through the semester, and generative and discriminative methods. And if you look at neural networks, I mean, the first week was essentially us having a crash course for those of you who had not taken a course in machine learning. And we introduced all these tools without sometimes going into too much detail because many of you have taken courses in machine learning before and you built a neural network. So this is something which we actually did not spend much time on. But then we went on and we linked this with a solution of partial differential equations. And the thing then that I would say that I'm a little bit biased here, obviously, that neural networks that solve differential equations are perhaps one of the most direct applications of deep learning to the physical sciences. We looked at physics-informed neural networks. We discussed all these different mathematical entities which enter and define neural networks. We, with pins, when we discussed that, we have a typical partial differential equation, which is the difference between the left-hand side and right-hand side, normally squared. And then we had the boundary conditions, but we can also have we can impose specific symmetries. We can impose initial conditions. On the example which we looked at on the heat equation, we had the differential equation itself, which we optimized. We had the boundary conditions, and we had the initial conditions. And then clearly automatic differentiation plays a very important role. Discuss network architectures, what the collocation points, training strategies, etc. So this was roughly up to week 3. Then the next 2 weeks, we spent some time on CNNs and looked at the mathematics of CNNs and looked especially for applied to images, which is one of the main fields of applications. And CNNs actually, so NNNs and CNNs and recurrent neural networks, actually elements which you can think of building blocks. Like if you look at GANs, you can set up 2 CNNs against each other. You can set up 2 recurrent neural networks against each other, etc., etc. If you look at autoencoders, it's the same. You actually, the autoencoder, you have the encoder part, which can be a CNN, and a decoder part, which can be a CNN, or just a plain neural network. So the CNNs, they are actually excellent at identifying spatial patterns. And especially for those of you who are more into, let's say, detector science, where you have pixels, images, which then can represent the energy which has been deposited in a detector. You can then reconstruct what kind of event this was. Then we had the RNN part, the next 2 weeks, week 6 and 7. And then we went through the standard vanilla one, which is a simple one based on actually a simple neural network, typically one layer, hidden layer. We went through the back propagation through time, discussed vanishing and exploding gradients. And then we had the more advanced ones, the LSTM and the GRU gates, which are often better when you have, because the RNN, the vanilla one is actually pretty heavy to train. So time series forecasting is actually one of the big applications here. PCA, the encoder decoder part, the bottleneck is actually it's not a bottleneck in the calculation, it's actually you narrowing down to a latent space. And then we have the denoising of the autoencoders, and we can have convolutional autoencoder architectures. And we also showed a close link with PCA, the principal component analysis, where if we have a linear autoencoder, this is exactly the same as a principal component analysis without a kernel PCA, non-linear extensions. Then we looked at the latent space visualizations and obviously applications. Transformers was the final part, which we went rather quickly through. That could be a course by itself. Actually, many of these methods, like if you look at CNNs, RNNs, and neural networks, could be a one semester course, only by themselves. Then we went to the generative methods, and the goal is actually for the generative ones, when you have a tractable or approximate probability, is actually to learn a probability distribution from the data, where you have some parameters theta, and you want to approximate that to reproduce the data. You have explicit versus implicit density estimations, explicit Boltzmann machines, variational autoencoders, diffusion models, implicit GANs. And the energy-based model is a Boltzmann machine, and that's based on the Boltzmann distribution. And you use Monte Carlo sampling and Gibbs sampling. So the Boltzmann machines we discussed were actually defined by restricted ones. You have a one visible layer and one hidden layer. We set up the contrastive divergence, where you have one expectation value, where you just take the log of this function here and simply run over the data you have, and then one where you have an expectation value, which is defined according to data points extracted from this distribution. You can, this has actually been abandoned, deep Boltzmann machines, because they are heavy to train. And then we have different things we went through with Boltzmann machines. We actually spent some time on implementing an RBM from scratch, because that gives often a nice way to look at the other methods. And if you're interested in quantum physics, it has actually been used in quantum many-body calculations. But then there is a direct link to quantum machine learning, where we have quantum Boltzmann machines as one of the more interesting approaches for machine learning applied to quantum technologies. And then we have the variational autoencoders. This is the function we want to learn. And this relates to the latent variable Z here. We have the objective function, which we are optimizing. So this is the function we want to optimize. So it's the gradient of this one. We discussed the tricks on how to do that. And we also discussed the different ways of setting it up and applications. But the applications were mainly done to the MNIST data set. And finally, diffusion models. This is normally the, one of the state-of-the-art methods. It's stable training versus generative adversarial networks. It's applications in many fields: molecular structure, protein folding, life science, etc., etc. So these methods are used widely in many different fields. So we went also through diffusion codes. And then finally today, we had a very short excursion into the basics of GANs. We mention a little about this Wasserstein GANs and also conditional GANs, but this is something which we have left for you for self-study if you want to dive a little bit deeper. And then clearly this is just the summary, etc., etc. So, and this is just a roadmap of what we did. You can take a look at these slides. But I wanted to say something about some perspectives. So this is roughly what we hope you have been able to see through the course. So the kind of overarching goal, I mean, my teaching goal with this course is actually that you see the mathematics and the practical implementations. So this is a course which doesn't focus only on the mathematics of the methods, but it also has a lot of codes and where you can look at practical implementations to apply state-of-the-art deep learning methods. So the course is essentially deep learning methods. Deep learning methods, discriminative and generative ones. So discriminative skills, I mean, derive and implement backpropagation, build your networks using PyTorch. We have people who actually build them from scratch. That's a semester-long project typically. And then we have other people who actually solve ordinary differential equations with neural networks. We have looked at autoencoders for data reductions and a brief excursion into transformers. And then we looked at Boltzmann machines, variational autoencoders, diffusion models, and today GANs. And obviously, we hope that you are able to see how you can apply these models to problems in the physical sciences. I mean, these models, we are not limited to the physical sciences. We've had people taking this course which come from economy and which want to use the same models in financial modeling or medicine. So there is, although the course is called Advanced Machine Learning for the Physical Sciences, this is just a title which we had to come up with, because if we just call it Advanced Machine Learning, people would say, hey, this is something you should tailor to many, many other different fields. So we try to restrict the examples to physical cases, physical sciences. But there's nothing which hinders you in using these in other disciplines, whether you are in the humanities or social sciences or life sciences and medicine in particular. Some perspectives. Oh, I see this one. I didn't see that one. If you're doing physics, many-body quantum systems, the neural networks actually are some of the best ways of solving quantum mechanical many-body problems. You get results which are on par with the best many-body methods. High-energy physics, event generation, fast detector simulation with GANs and diffusion models are typical examples. Astro and cosmological data, these are examples of where these methods have been used. And actually here, in addition to phase classification, I have to remember what I put in here. I have to look it up actually. So I've been also working on you classifying phases. Let's say if you're taking spin models like the Ising model, if you're familiar with that, that has a paramagnetic phase and a magnetic phase. There's a phase transition. And you can take images from the distributions of spins and train a neural network or CNN to recognize whether this is below or above the critical temperature. So people are actually using this in both condensed matter and high energy physics. So those people are interested in the phase transition from hadronic degrees of freedom to quark-gluon plasma. They're actually using modeling to be able to determine whether that is a phase which corresponds to hadronic phase or not. If you do chemistry, there is actually a lot of interest, especially if you are thinking of reactions like catalysis. So we have a big experimental activity in the chemistry department on catalysis. And many of these reactions are now actually modeled with machine learning methods or deep learning methods. Quantum chemistry is actually being used in popular quantum chemistry methods like the copper cluster theory, the CCS, or density functional theory. Physics-informed neural network for actually solving quantum mechanical many-body problem and the time evolution of the system. So Another topic which we have not discussed is actually graph neural networks. This is also a very hot topic, but there's a limit to how much we can squeeze into this course. So I wanted to do that, but I never found the time to do it. I'm sorry for that. Also, many of the topics which I present, they also reflect what I've been doing research-wise. So I try to present things where I think I can say something meaningful. In mathematics, there's a lot going on. One of the topics which I think is really, really hot, and this is my own bias, is actually uncertainty quantification. That's because if you think of many of the calculations which we make, you'll be surprised when you look into scientific articles that very few of them quantify the uncertainties in the parameters. In a certain sense, that's a little bit wasted because you run a calculation, nice, but what are your uncertainties? And this is actually a big field with Bayesian deep learning, which is, if you're interested in that, I really recommend looking at it. Operator learning is also a very hot field if you're interested in differential equations. And then if you look back at what we discussed in the beginning of the previous lecture of the inverse problem, where we had the probability distribution and we had a function where we can calculate the inverse of, and then we could find a new probability distribution. That's an example of an inverse problem. And that's a very, very important problem again. Symbolic regression is also very, very popular. If you look into geoscience, it spans everything from weather and climate, seismology, CNNs and RNNs for earthquake detection. It's a very hot topic. So the Department of Geoscience here has a big activity on climate research, but also seismology. You have remote sensing, reservoir studies. This is actually also something which went out of the slides. I didn't see that before now. But reservoir studies is also a very popular field of studies. It's almost unlimited what you can do with these methods. If you move on to bioscience, there we also have a lot of activity in pharmacy. We have using these methods on drug discovery. We have that on RNA and DNA modeling. Protein structure prediction is actually the Nobel Prize in 2024 in chemistry. Single cell genomics, actually variational autoencoders and diffusion models are very, very popular models there. Medical imaging, CNNs. I'd say this, if you think of the kind of societal immediate benefit of deep learning methods, I would say medical imaging is really one of them. So you're probably familiar with a Chinese company called Alibaba. So Alibaba was one of the first ones to develop advanced CNNs models to be able to spot whether a tumor is benign or not. And one of the reasons for that is that China has a lower coverage of medical doctors per inhabitant than we typically have in our countries. Which means that if you think of a pathologist, and this is actually not a problem only related to countries in the global south, but it applies to any country. It takes a life to train a pathologist. So the pathologist is the one who actually goes through the screens and the data and look at whether this is a tumor which needs treatment or not. And it can often take days. With CNNs, you can screen out the benign ones, the safe ones, and also the clear malignant ones quickly. And then you can focus on the ones which are more dubious. And then you can bring in advanced machine learning methods together with the lifelong expertise of a pathologist. So all hospitals actually suffer from the lack of pathologists, and it takes a life to train one. So CNNs for medical imaging is really, if you think of societal benefit, this is huge. So when I look at the impact of what I do is solving quantum many-body problems, and you just mumble, what are you doing? I'm using deep learning to solve many-body problems. Yeah, but what can you use that for? And then you put up medical imaging. That's pretty cool. And then you have perspectives, agentic AI and reinforcement learning. This is really hot topics. And I have put up some perspectives. Take a look at it. So where I am focusing most of my research into is actually quantum control. That's my main research with reinforcement learning and agentic AI. So you have tons of places where this is now being developed. And that's going to be the next generation of, how to say, AI and machine learning methods applied to scientific problems. So take a look at them. I'm not going to read. I hope you don't get offended if I don't read every word here. But take a look at it because I just listed a set of perspectives here for future activities. Actually, when you do quantum control here, this could be quantum control of quantum technologies. So you making a sensor means that you need to initialize the system. You need to study its time evolution under the influence of an external field, which you want to measure. And then you have to make a measurement. So these three elements are elements of quantum control. You can have a theoretical model, which does a pretty good job. But then you want to link this with experimental data. So you can have a setup where you have theory and experiment, which are then linked together with agentic AI and then reinforcement learning. So you can really optimize, for instance, the experimental setup and also use experimental data to improve your theoretical models. People use this for detector design nowadays. It's pretty common. Plasma infusion, a really hot topic. And I put up other things which we haven't discussed, like graph neural networks. This is a topic which I always feel bad about because it's a very interesting topic, but I was not able to find time for it. I'm sorry. I mean, there's a limit. And then clearly scientific large language models. It's a very hot topic. Yeah. Could you say again? Yeah. Absolutely. Absolutely. When you, yeah, because I would typically want to train a probability distribution. And then I can say, what is the probability of A given B? And that's very important. So what you're seeing now is that when you do science, these methods have become indispensable. And it means that you need to have a good training in statistics. Obviously, the methods which pertain the mathematical tools like linear algebra and optimization tools. And then clearly efficient coding, automatic differentiation is just essential if you want to be effective. And many of these things, so I've actually built a quantum control program for reinforcement learning using Claude. So I took all my C++ codes for the many body physics, and then I translated that one into a Jupyter notebook. And then I kept adding things which I had written, but then I did not have a library for reinforcement learning. This library exists. There are colleagues of mine who developed it. And then I just asked Claude to integrate that library with my programs, but step by step. So when you have all these tools, you have the possibility to actually enter this type of research in a much quicker way than you would do previously. So these are just some perspectives for future work. And in fields like particle physics, especially, this is actually, all these methods are widely used. And you probably, those of you who do a master's thesis or PhD in particle physics, you probably encountered most of these methods. Okay, so that ends this year. It's always a great pleasure to meet all of you, get to know you. It's always sad when the semester is over, but I guess you would like to do something else than just listen to me again and again. So thanks for your attention, guys. And let's take a small break.